Hello guys, welcome to today's class where we'll be looking at the Pascal's triangle. Now, in the last class we talked about how we can actually expand using the Binomial Theorem, and then we said there are two methods that we use to expand, aside our basic expansion, which of course we do not want to use at this stage. We have the Pascal's triangle and the combination method. In today's lecture we'll be looking at exclusively the Pascal's triangle. Now the Pascal's triangle is basically a triangular array of numbers that is what is formed or is constructed by summing up adjacent elements or values in that system. So it is actually a form of what? Of expressing our binomial coefficient. It is a form by which we actually get our values for the binomial coefficient of various powers, that is of expansion at various powers. So it was actually it was named after a French mathematician from the 17th century known as Blaise Pascal. Yes, the Pascal that here, the very popular Pascal that we know. Yeah, Blaise Pascal. So it was named after him. And then it talks about how we can actually use a triangular array of numbers by summing up these adjacent values to form our binomial coefficients, which can now be used for any particular expansion at any particular index. So we'll be looking at how it is formed. For the Pascal's triangle. Now, to start the Pascal's triangle, the first thing we do is start with what? 1. We write our 1. The next thing we do, we start with 1 and then we end with 1. The next thing we do, we always start with 1 and we always end with 1. But because we are looking at how we are summing up adjacent values, we say 1 plus 1 here gives me 2, and then I make sure I end with 1 again. I start with 1 again, 1 plus 2 giving me 3, 2 plus 1 giving me 3, I end with 1. I start with 1 again, 1 plus 3 giving me 4, 3 plus 3 giving me 6, 3 plus 1 giving me 4, I end with 1 again. I start with 1 again, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, ending with 1 again. I start with 1, 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6, end with 1. The same thing, I keep on repeating the process until I reach the particular power that I want to stop. Here we'll be taking a value of 10, we'll be stopping at 10. 15 plus 20 here, 35, 35, 21, 7, 1. Moving forward, we have 1, 8, 56, 17, 56, 28, 8, 1. 1, 9, 36, 84, 126, 126, 84, 36, 9, 1. Last but not the least here, we have 1, 10, 45, 120, and 10, 252, 210, 120, 45, 10. So if you look at this, you realize that what? It is basically just a triangle, the triangular array of digits that are formed by adding adjacent values. We add 3 to 3 to give us 6. We add 4 plus 6 to give us 10. We add 5 plus 10 to give us 15. And then the sequence goes on and on and on like that. So that is just what happened. Now, for each of the powers now, how do we now allocate each power to each of them? We know when we have a power 2, for power 2, this is for power 2, this is for power 3, this is for an exponent 4, power 5, 6, 7, 8, 9, 10. So we definitely have more than this. We can do as much as we like. We can actually keep on constructing forming our table till we actually reach our desired exponent or expansion or coefficient, as the case may be. But this is just a draft of how we actually develop the Pascal's triangle, how the Pascal's triangle is actually constructed. So this is what happens. So this is for 1, and then this is what we do. Now, how do we now apply the Pascal's triangle in solving questions? That we'll look at. How do we now apply the Pascal's triangle in solving questions? So that we'll be looking at in the next class, and we'll be trying to analyze how we can actually use these coefficients that are derived so actually expanding our binomial values, our binomial theorem. So see you next class. Enjoy yourself.